In this video, I will discuss the kinematics equations. As you know, the kinematics equations describe motion with constant acceleration or no acceleration. The first equation is if you have an object that is speeding up, this is the position versus time graph, this is the initial position, and if you draw a tangent at time zero, that is the initial velocity of the object. And you know that this is a quadratic function, and I explained to you in the calculus derivation of this equation. I explained to you where all these terms come from this equation. If the acceleration is constant, you know acceleration is dv dt, is constant, and from here we got that. So if you take the derivative of a quadratic function, you get a linear function. So you know the velocity versus time is a linear function, and the slope of this line is the acceleration, and this is the equation. This is equation 1, and this is equation 2. So the derivative of equation 1 give you equation 2, and you could check it out. Remember that the velocity is dx dt. So if you take the derivative of this is what you get. These are the most important equations of the force kinematics equation that we are going to study, because these come from experiment and from calculus. If the acceleration is constant, we integrate this equation 2 times and we get that one. If we integrate this equation 1 time, we get this one. So this is what you have to keep in mind. These are the 2 equations, but there are 2 more. This one and this one. B naught plus B, initial plus final, times T. In this video, I will show you how to get these 2 from these 2. Okay? So we have these 2. This is equation 1 and 2. And we want to prove this one. That's what we want to prove. Okay. So we are going to take first step, solve for t in 2. And we get t equals b minus b naught divided by the acceleration. Second step, substitute t in 1. And this, I will move the x naught to the left side for convenience. And now you are going to substitute t. and now t is a square. Don't forget this square over here. And now you can see this is a square, so it's going to cancel one of them. We put the a like this, and over here is 1 over 2a, because a and a squared, you only have one left, and you have b minus b naught squared. Now b minus b naught is a common factor. B minus B naught and A is a common factor, so I will take it out. B minus B naught over A. And what if left over here is B naught? And what if left over here is 1/2 B minus B naught? Because the other one, there are two, because it's square, the other one I took it out. And now I have B naught, and now we'll distribute this. And 1 minus 1/2 is positive 1/2. So you have positive 1/2, and I have this term over here. So B naught minus 1/2 B naught is 1/2 B naught. And as you can see, I could take now the 2 as a common factor. So it's 2a. Let's put a parenthesis here. And now you have b plus b naught. I put it in this way. I put the b first because I had the b here first. And if you remember from algebra, a minus b, a plus b is a squared minus b squared. If you don't know this, just distribute this, and you're going to see two terms canceling out. Okay, so I get this equation. And now I multiply by 2a. And now add b naught squared. And you get and this is the third kinematic equation. This one, you use it, and you try to use it anytime that time is not given. Because as you can see, time is not present in this equation. And the reason is because that's what I did. I took time from here and substituted in 1 and get this. So let's put that. So that's how I got it, by substituting the time into the first kinematic equation. Now let's go to the second one. Okay, this is the one that we want to prove now. From these two, we want to prove this one over here. So as you can see, this equation doesn't have acceleration. So it's kind of the same procedure that we used in the previous one. Step 1, solve for the acceleration in equation 2. So acceleration is b minus b naught over a. And we are going to substitute the acceleration into 1. Again, I will move the initial position to the left for convenience. And now here in the acceleration, I'm going to put b minus b naught over t. This is t over here. I don't know why I was thinking in the previous exercise. So a is b minus b naught divided by t. b minus b naught divided by t is what the acceleration is. Over t squared. So you can see 1t cancel. I got x minus x naught equals b naught t plus 1/2 b minus b naught times t. I will distribute this. So it's 1/2 bt minus 1/2 b naught t. And these two are common factors. So 1 minus 1/2 is positive 1/2. And now I take the half and the t as a common factor. And this is the third equation. The half and the t these are like terms. 1 minus 1/2 is 1/2. And these are common factors, 1/2 t, 1/2 t. So I'm left with b naught plus b. This can be rewritten and this can be rewritten as this, just putting, because this look like the average velocity, the final minus the initial divided by 2 times t. And this is equation number 4. And this equation is very confusing. This equation is very confusing. And the reason this equation is very confusing is motion with acceleration, but the acceleration is not in the equation. So this is useful when acceleration is not given. The previous one was useful when the time is not given. But why is this confusing? Because this looks like the displacement. It looks like the displacement is a linear function. And the slope is 1/2 b naught plus b. And that is wrong. That is wrong. This is wrong. And the reason people get confused is because this b over here is a function of time. So you have times t, and then you have 1/2 b naught plus, and this is b naught plus at. You see, that's the velocity later in time. So if you have a linear function, this is a linear function of time, times time is not linear, is quadratic. So you have t times this t is t squared. So this equation is very confusing because it looks displacement is a linear function of time and the slope is 1/2 b plus b naught. But that is wrong because this b is a linear function of time. So that b is equals to b naught plus at. So remember, the only thing constant here is the acceleration. Acceleration is just a number that does not change in time. The final velocity is a number that changes in time. Obviously, t is the variable that keeps on going, and the position is the other variable that could change in time. So these are the four kinematics equations that you use to solve problems. Um, the most important one are the first two, because that's how you build your knowledge. From these two, you get the other two. From 1 and 2, you derive 3 and 4. 3 is you get rid of the time, and 4 is you get rid of the acceleration. The fourth one, this is b, the velocity later in time. This itself is a function of time. That is equation number 2. So if you have a linear function of time times t, you get a quadratic function. Number 4 is not, it is not a linear function. It looks like it, but is not. So these are the four kinematics equations. These are the equations that you use to solve problems. And the last two are very convenient. And number three is very convenient because it's going to show up in conservation of energy. You are going to see how important that equation is. It's very important you understand each of them and what variables are present or are not present in each of them.